Hello, we are the Capstone design team of 2015, and this is our virtual integrated training environment. It's a project we've been working on over the past 2 semesters. My name is Michael Lewis. I'm aided today by Faisal Ashur, and in the crowd we have Karina Rusnak, Matthew Connolly, and Jason Millat, who all worked on this project in partnership with Eastern Virginia Medical School. And we are part of the Department of Modeling, Simulation, Visualization, and Engineering at Old Dominion University. Main overview, we're just going to be going through the introduction, just giving you a little backstory of how exactly the project started and what we were working with in the beginning. After that, we'll be looking at the system architecture, describing all of the components of the system, giving you a quick run through of what exactly our new system will be doing. We'll provide a few brief examples of how a message would be going through the system, and just an example of a drug transferring all the way through and the entire architecture. After that, we'll give a little bit more detail on the system devices, and then we'll be concluding our presentation where we'll go into a demo in the cave to show off our progress so far. All right. First is the introduction, where we're going to talk about what our overall purpose is, talk about the current system that they currently have at Eastern Virginia Medical School, and talk about the improvements that we're going to be making in our new physical system, as well as our design goals that we kept to over the past 2 semesters. The current system that they have at EVMS is a medical scenario with a mannequin, a student, an instructor, and a technician. As the student goes through the scenario, they perform a variety of operations on the mannequin, which the instructor will either take notice or the student will announce, and from there the technician will make changes to the mannequin's physiology based on the actions of the student or the instructions of the instructor. There's currently no direct communication between objects, and when devices are used within the system, they are completely physical, real devices. The new system that we're planning to implement will incorporate some virtual devices in replacement of the real devices in order to make it easier to acquire each of the devices in the system. And to make sure that communication is simple and easy, we will be implementing a new communication system that will allow all devices that we've created to be placed into the system and cooperating with the previous current system without any extra overhead or issue. The main design goals that we wanted to go with first was integrated communication, making sure that every device, every component in the system communicated without delay, without seams, without any complete issues, or without needing to personally notify and have that vocal communication between each other. Another thing that we wanted to do is make sure that the system we created was expandable, making sure that items can be added or removed if you prefer at any time during the simulation, or you can create new items to add to the scenario if you'd like. And lastly, we wanted to make sure that it was user-friendly. The scenarios that they go through at Eastern Virginia Medical School are typically 10 minutes or less, so we want to be sure that you're not taking a 2 to 3 hour tutorial in order to learn how to use these new devices that are in the system. In order to accomplish this, we made sure that the devices are as close to the real-life objects as possible. The new physical system that we're implementing, we're just going to go through it piece by piece. One of the big things is the virtual environment, which will be a 3D backdrop that the student can operate in order to just add to the immersiveness of the entire simulation. There is the mannequin. In this situation, it will be the Layerdall Simman mannequin, but this is easily replaceable by other mannequins if the user would desire so. And we do want to specifically note that nothing about the mannequin is actually changed in this system. Should you want to revert back to the old system, or if you don't want to be using a particular device, the Simman mannequin that was already in the system does not change in its functionality. It does not change in how the student or the instructor would interact with the mannequin. This is to be as seamless as possible. The student and instructor still perform their basic roles in the entire scenario, although the student should have a few more tools to work with in the new system, with the IV pump and the patient monitor added to it, which allow it to communicate directly to the Simman and actually communicate with the program, adjusting its physiology as time goes on, as opposed to needing to consult a technician. But the technician is still there to make any changes that need to happen with the Simman program, and to make sure it's capable of monitoring all the actions that are occurring in the system. There is a management program that routes all messages sent by the IV pump and the patient monitor that allows the technician to see everything that's going on in the system, even though it may not be as involved as it was previously. This is kind of a quick example of the virtual environment that we're planning to create that we'll be showing off in the demo room to the side there. We have the two tablets there that are showing the IV pump and the patient monitor, the virtual environment adorned on the walls, and as well the Simman Manikin that's always been part of the simulation on its position. You can see that it doesn't really interfere with the Manikin itself, and you can still operate on it. And for this communication system that we've set up, we wanted to make sure that everything's wireless so that there's not extra hazard that you're going through as you're trying to operate with the Manikin. Next, we'll be talking really quickly about the system architecture. We'll be covering the star topology, which covers most of the expandability of the system, as well as the communication system, which is kind of one of the major components of the design that we've done, including the communication program and also the software controller. The star topology is designed so that each item can be easily added to and removed from the system. There's only one device that all other devices send their messages to, and that is the software controller. It acts as the main hub and reroutes all messages where they need to go and figures out everything's destination from a preconceived file known as a configuration file that we'll be covering a bit later. We're going to run through a quick demo right now, or a quick example that shows how exactly a drug would go about the system and affect the physiology of the Simman. First, the student would start an infusion at the IV pump device, which, since it's connected to the controller, would immediately send a drug message. The controller would consult its routing tables and realize that it needs to go to the Manikin device and forward the message thusly. The Manikin will receive it and adjust its physiology in order to change any heart rate, blood pressure, different waveforms, just any matters of its health. And if any of these changes are immediately noted or upon being noted, its updated parameters are sent back to the controller so that it can look at its routing tables once more and realize that these parameters need to be sent to the patient monitor. They will be forwarded there, and the patient monitor, upon receiving the message, will read it and adjust its own display. Even though this matter takes it in small steps, do understand that this entire action will be done in a matter of seconds in the actual simulation, as opposed to the student using the IV pump and then telling the technician what he's doing, and the technician has to manually type something in. This is all handled automatically now with our system. What we have here is a detailed illustration of our architecture. This covers each individual component of all of the devices that we're currently including in our system. First and foremost is a communication network that we will be communicating through using the communication programs, which all these programs are completely identical across each of the devices, so that if a new device needs to be added, it just needs to incorporate that communication program and it can be made as quickly as possible. On the next piece, we have the interpreters, which essentially take messages or receive messages from the communication program and also send messages to the communication program, and that's part of a base interpreter that's existent on all devices. Another half of the interpreter is more device specific and will essentially read from the program that it's attached to in order to figure out when to send messages and what messages to send, as well as when it receives messages from the communication program, it will interpret them and translate them into code that can actually be executed by its respective program. And of course, we have the respective programs that give each device its unique identity and its unique function within the system. Sometimes these programs can come already built, similar to the Laerdal Simman program that I have, and sometimes we can design them ourselves that will be demoing just like the IV pump and the patient monitor. The software controller is one of the more notable parts of the system, in which every time it receives a message, it will consult the configuration file and reroute it out to its proper destination. It acts as the main hub, and it determines the destinations, and it also starts up the entire system and is capable of shutting it down if need be. The configuration file is another important part of the management program. It essentially lists all the devices that will be in the system, all the messages that will be transferred, and it also can note what messages and what types of messages are being sent throughout the systems and what data they are and are not allowed to contain. Right. And now we're just going to go through a little bit more specific example of the same drug message being transferred throughout the system. First, it still starts with the student interacting with the IV pump device, and upon entering in a drug, a rate, and the volume to be infused, and hitting the start button, the interpreter will immediately realize that it needs to send out a message of that drug and that drug rate, which it will encapsulate and pass to the communication program, which will send the message over the communication network to the management program's communication program, which will then pass it to its own interpreter, which will pass part of the message, most notably its header, to the actual management program that will read from its config file and realize what routing table it's using, and send back to the interpreter information on where exactly to send the message, who will pass that to the communication program. And do know that in some examples, the communication program is more than capable of sending a particular message to more than one recipient. However, in this example right here, it's just sent to one. So here it's going to go once again through the communication network to the Simman computer's communication program, which will be passed to its interpreter. And once it realizes it's a drug message with a drug rate, it'll process that into a line of code that can be interpreted by the Simman, which upon receiving the message will react according to the scenario that the Simman itself is running, adjust its physiology, and upon these physiology changes, these will be read by the interpreter and encapsulated into a message to send back to the communication program, to the management program, where it'll once again consult its routing tables and pass a forwarding message on to the interpreter to let it know where to send its messages to. After one last go through the communication network, it'll arrive at the patient monitor's communication program, where it'll pass this information on to the interpreter, and it'll let its device know of the values that have changed and what the values have changed to. And upon that, it'll adjust its display. And now we'll be talking about system devices, in which Faisal will be taking over here.
Hello. So I'm going to talk about the system devices which we have in here, the Manikin and the two devices, the patient monitor, the IV pump. Then I'm going to talk about the device modes. First is the Manikin. The Manikin is being used in this system is the Lurdo Simman. However, any other Manikin can be used, and that's exclusive for Simman. The goal of this system is to minimize the role of the technician in the simulation. That means will happen through if the IV pump being infused with the drug, it will send it to the Manikin. The Manikin will identify this drug and change its physiology currently. The Simman will send its vital to the patient monitor that contain parameters and a waveform based on the physiology of the Manikin, and keep looping through that until it receives a new update from Simman. The two operation mode we have, which is the integrated and independent. The integrated mode is used with the virtual environment and the Manikin, and the independent one is used outside the virtual environment. The other devices we have, it's component determine the new device component being added to the system that will have the same communication pathway of the current devices, as well as an alternative pathway through the model system. The model system will have the ability to provide the system with the system log and the positive and negative feedback and the optional limiter. So the limiter of the option, if the IV pump, the student will inject the system with a drug that is not listed through the optional limiter, it will give a positive or negative feedback to the student, showing that is being outside of the limiter. The patient monitor being used in here is based on a real medical patient monitor with the same functionality of built through the GE-4000 patient monitor that have a pre-programmed layout. The patient monitor is being displayed either an app on a tablet or in a monitor or projected through a wall. The user will identify these parameters through the configuration file at the start of the simulation. So once the simulation starts, the Manikin will send these parameters to the patient monitor and send the waveform and the parameters and keep looping until it receives a new VITE from the Simman. The IV pump being used in here is built on the functionality and the user input of a real IV pump that's built from the bottom A+ infusion pump. The user will interact directly with the IV pump to send the infused drug and drug rate to the Simman. So once the user insert the the drug through the IV pump, it will send the drug message infused to the Simman. This message includes the drug type infused and the rate being infused to the Manikin. In conclusion, the VITE is being built reason to integrate with the Manikin to provide a realistic simulation environment with reducing the cost being used for not using real medical devices, as well as the unique and one of the only communication being built that will allow the Simman to communicate with the virtual devices. The user will have the ability to interact with the devices other than the patient as in real life. In final, it will have also the communication network will have the ability also to add a new devices and a software to the system easily. Also, we will able to create a Manikin-based training with a seamless training environment for the user.
So continuing our presentation, this part is our virtual integrated training environment, short for VITE. This is the project demonstration. So for the overview, what we're going to start with the initialization. We're going to then head to the patient monitor's running mode, and then the IV pump's running mode. Then we're going to talk about the disconnection of the system, and that's it. So in initialization, it's many steps. The first step is to start the software controller. And the second step is to select the configuration file. The third step is to connect all devices. And the fourth step is to initialize all devices. The fifth step is to receive confirmation from all the devices. And the sixth step is to start the simulation. For the first step, start the software controller, you must run the management program to open the software controller's user interface. And this is what the software controller user interface looks like. So you'll select a configuration file from this drop-down menu. And these configuration files, you can have up to as many as you want. You create them. When you select your configuration file, you click Connect, and that will, all devices included in the configuration file are now able to connect to the management program. Well, now we're at the initialize devices step. When all devices are connected to the management program, the software controller sends initialize messages to the corresponding devices. The software controller text is gray until all the devices finish initializing. This lets the technician know that he is not to connect yet because all devices have not connected to the system. To initialize all devices, we're going to start with the demonstration of the IV pump. Since the IV pump has user interaction, you can't just start using it without having finished initialization first. If the student was to use it, they could send a drug and the system would not be set up yet and the management program would not receive it. So to avoid this, what we do is we stop the device from starting by making initialization screens to ensure initialization finishes first. So what you do first is you launch the application from your device interface. So what he's doing right now, he's going to launch the application, and the IV pump will display a list of the 10 IP addresses or computer names. Right now, what you see on the screen is the form with the IP addresses, but on the tablet right now, you can see that we have it set so the computer's name shows up. So you'll see management program. You click the management program or whichever computer IP address you want to connect to, and then it's going to come up with the initialization screen. After the IV pump connects, it receives an initialization message from the software controller. The initialization message will include a list of drugs. And these drugs are used to populate a list inside of the IV pump, which the students are able to infuse to the Simman. The format of the drug is, the first word is drug, and then continues with the list of drugs, up to 3 right now. The IV pump sends a done message to the controller and will remain on the initialization screen until all of the other devices in the system are connected. So right now the management program received all the done message from all the devices that connect in the system. If one device does not connect, it will not allow the IV pump to start. And so that was a demonstration of that. So we're going to go to the patient monitor. The patient monitor, right here, we have it on a monitor instead of a tablet, so we can show a little bit of diversity since the IV pump is on a tablet. What it will be is a black screen once you launch it from your tablet interface, and it will connect it will automatically connect to the management program. Since there's no user interaction and it's just a display, there's nothing stopping the patient monitor from starting when the simulation starts, because no one can interact with it and mess it up. So the patient monitor will receive multiple initialization messages from the software controller depending on the configuration file. It can receive waveform messages and statistic messages. When it receives these messages, what it does is it creates the layout according to how many waveforms it received and how many statistic messages it received. So for example, the black screen shows and it populates the names of the waveforms and the statistics according to the initialization messages. So now the initialization of Simman. Simman is very automatic because the program is already made and we just basically have to connect it. So once you launch Leap to run the Simman, you run the Simman's interpreter and select the Simman from the drop-down menu. You would click Connect to connect to the software controller. So as you see, we selected Michael's PC to choose the Manikin, and we connect to the software controller. And then automatically, the initialization message is received with Simman, and what Simman receives is he receives everything in the system. So he'll receive the drug message, he'll receive the stat message, and he'll receive the waveform message. When finished initialization, the interpreter sends a done message also to the software controller so that the software controller knows that that device is done initialization. The interpreter receives a start message when all devices are connected and the simulation begins. Right here is just the interface at Simman. So this screen is populated from the messages he received. So in this example, he received ECG, ABP, SpO2, and etc. So now, since all devices have been initialized, what we're going to do in the software controller is we're going to go ahead and press connect. As you can see, the text in the software controller has turned green, letting the technician know that all the devices have connected and everything's a go. And initialize, so everything's a go. So the technician will press the connection button and start messages will send out to all the devices that are already connected to it. So back to the IV pump. When it receives that start message sent out to all the devices, you can now click the check button. The check button, basically, all it does is enables the start button. If you click the check button prior to receiving the start button, it will do nothing. It will check and it will still disable the start button, so you could not start the simulation. So the student could not interfere with the IV pump. If all the devices have connected in the system, the start button will be enabled. So the student can come around, well, the technician can come around and press the start button, and then the IV pump device will start. So this is what the IV pump for main screen is. It shows in off mode. As you can see, we connected the whole system, and so what happened is the patient monitor received its information from Simman, and it went and started to show the parameters. So this is what it did. It was blank. The monitor will automatically connect. It did and initialize. It received that start message, and it continuously receives statistic and waveform messages from the Simman. You can set it to a certain rate. You can make it 2 seconds, 5 seconds, 10 seconds, depending on whatever you would like. Right now we have it at 2 seconds. It receives every statistic and waveform messages, and then it populates onto the monitor. The IV pump in running mode. This is a longer process because it mirrors the original real IV pump. So you have to go through multiple screens to get to a drug infusion. So the first screen is the off screen. And what you're going to do, you're going to press the on and off button. And that's going to go to the clear settings screen. What it is if you press yes, it will clear all of the settings. It will clear all of the variables such as rate, volume to be infused, volume infused. Any numerical value that you have to enter is going to be set to 0 default, or previous settings will be erased. So you go ahead and press yes. Yes is going to take you to the main home screen. The main home screen basically has pump A, pump B, and if you have a current infusion, it will say stopped. If you have, well, it will say start if you have a current infusion. If you don't, it will say stop, and it will have the corresponding rate and volume infused on the screen. So to begin an infusion, you can press the A or the B buttons on the screen. The triangle buttons is what indicates what's on top of the triangle button. So if you press the triangle below A, it will go to pump A. If you press the triangle below B, it's going to go to pump B. So once you do that, this screen shows you what we received from initialization. This list with 3 drugs we received from the software controller. So basically, this is where that populated list went during initialization. So obviously, initialization is very important because if that step was messed up or skipped, there would be no drug list and there would be no drug infusion. Nothing would be working because wouldn't have nothing to infuse. So what the student would do is they would choose a drug from the drug list by clicking it, and then they would press the enter button. What this then does is assigns the drug to be sent. It does not send the drug. You have to first put in the values of rate, volume to be infused, and duration. Once the student enters these 3 values, you press the start button, and the start button is what sends these parameters and that drug that you chose to the software controller. The software controller then sends it to the Simman, and the parameters will adjust according to its physiology from the drug infusion.
Give me something for this pain. It hurts. It really hurts. I feel better now.
Well, the drug was received, the Simman got it. The technician controls the disconnection in the software controller. So what the user interface for the technician looks like is when he presses that connect button from the beginning to push the connect button that sends all the start messages, this screen is going to come up. So he now has the option to pause the simulation and to stop the simulation. If the technician presses pause during the simulation, what it's going to do is going to go to another screen that lets you either resume or stop the simulation. If the stop button is pressed, it goes to another screen and gives you 3 different options. The restart option, the select new configuration file option, and the shutdown option. The restart option starts the simulation over with the same scenario. The select new configuration file starts from the beginning and lets you select a new configuration file or a new scenario if that's what you would like. So you can add more devices, disconnect devices. This is where all that would be defined. The shutdown button allows everyone to disconnect and the management program shuts down. So the simulation initially is over because it can't continue without the management program. But the other devices will be able to function on their own if that is the wish. Simman can still continue to be Simman.